had to wait until 1:45 to make sure any stragglers might come in. Next talk is, as you know, is by, you might know him, David Bowman G0MRF, creator of several projects on the AMSAT website and everything. As you can read, it's about Funcube Next. Over to you.
Okay, thank you very much, Chris. As we're at a meeting today where we not only have members of the AMSAT community, but we probably have some people coming in from the RSGB convention going alongside us, I'm going to do a little bit more of an explanation than I probably would when I come up with words like CubeSat and maybe things I would take for granted that you knew. I'll just try and explain a little more as I go through. So Funcube has been the name of a project since around 2011, and in the 10 years since we launched the original Funcube 1 or AO73, we've gained a certain amount of experience. In the last 10 years we've been part of 6 different missions, and in chronological order across the top there we started off with AO73, which is a 1U CubeSat, and in real life it's actually is that size. So that's a 3D printed version of a structure that we have here, but they're 10 by 10 by 10 centimeters. And they come in various varieties. Along the top we've got AO73, launched in November 2013, so coming up for its 9th birthday now. It's doing very well in orbit. The next project a year later was UCube 1, which was a project sponsored by the UK Space Agency, and we had a payload on board that one. That was a 3U satellite. So if you imagine 1U, 2U, put them together, oops, that way we've got a 3U satellite, so 30 centimeters long. So they all come in very standard sizes. Moving on from that, we took part in a project which resulted in EO79. That was a satellite that was a test and development satellite for testing sensors for the von Karman Institute of Fluid Dynamics in Belgium. And they kindly let us put a Funcube transponder on board that mission. And then we went on a few years later to do EO88, otherwise known as Naif 1, JO97, which is JY1SAT, with the sponsoring organization coming from Jordan. And finally, not a CubeSat. On the right-hand side, 44 kilograms, I think it weighed in, a microsatellite from the ESA Education Office. So even although it was just AO73 that was funded and managed and the project run by AMSAT-UK, we've actually been involved in a lot of different missions providing payloads for other countries who wish to put CubeSats into orbit. And I guess that says something about our reputation of doing things that mainly work, but as we all know, space is not easy. Of course, when you spend all that time making these satellites and getting people to launch them for you, hopefully at low cost, the moment you all wait for, probably with crossed fingers, is this. With no video at all. Space is difficult. Okay. So can we show that at all, Graham? There we go. Okay, so over the years, these 6 missions have flown on 5 different launches. AO73 was launched from Russia on a converted intercontinental ballistic missile. I'm quite glad now that that's one less available. Funcube 2, or UCube for the UK Space Agency, was also launched from Russia on a Soyuz from Baikonur. Very impressive to see that one go up. Admittedly, I've not been to one of these launches, but you tend to get them live streamed. EO-79, another Dnepr from Russia. And then we went on. Naive 1 was launched by the Indian Space Agency. I do love that shot of the Soyuz. That is really nice. And of course the one on the right hand side there, carrying 2 of the missions, JY1SAT and SAO for the ESA Education Office, was launched from Vandenberg Air Force Base on one of Elon Musk's Falcon 9s. So we've had a fair experience of building things and getting them launched on different agencies' rockets. And during that process, we've gained a fair amount of experience of what goes right and what sometimes doesn't go quite as planned. I want to spend the first part of this talk because experience is everything, and with a bit of luck, if we can get back from the cupola module, which I think is on the ISS, isn't it?
Keep talking.
Okay, let's do a talk about these things. CubeSats, absolutely wonderful idea. No professional rocket launcher wants to have an amateur radio satellite that may have been built by people who don't quite know what they're doing above a multi-million-pound satellite sitting right underneath it. You can imagine there's a lot of G-forces. If your CubeSat is just mounted in the under the fairing above somebody else's and it all falls to pieces because it hasn't been made perhaps by a group of students as well as it should, you don't want all that material crashing down on somebody else's $100 million satellite. So a chap called Bob Twiggs came up with this idea in the late 1990s, I think it was, at Stanford University. He said, well, to mitigate that risk to other people's satellites, we'll make the CubeSats and we'll actually put them inside very tough deployers on the rockets. So the idea is now that the deployers are very well known. They're made by people who know what they're doing. And if you happen to have a CubeSat inside that isn't quite as good as it should be, it rattles apart, but all the bits are contained in the launch pod. So, this is the way to get amateur radio satellites and educational missions into space with minimal risk to all the other passengers on the flight.
Don't use preview mode on the PowerPoint.
I think I've learned something already. Don't play the video at the end of the talk. So CubeSats are a phenomenon that have been around for basically the last 20 years. We've produced several of them now. AO-73 was the initial one. It took about 3 years from the initial concept, which I think happened in a bar at one of these colloquiums when we held them in Surrey. But it went on to good things. We managed to get some funding for that, and it was launched in 2013. If we have a look at the table here, we can see how well the satellites have done that we've been part of. AO-73 is still in orbit and working well. 8.9 years later, it was launched in November 2013, so it's just coming up to its 9th birthday. We can see that the batteries that are a part of this satellite, which are essentially the lithium-ion cells you find in, I think it's Sony laptops of that era, are beginning to degrade. So at the moment it's in a position where we keep it in telemetry mode for educational outreach during the illuminated part of the orbit. But when it goes into eclipse, we don't want to damage the batteries anymore, so we actually switch it into receive-only mode so the transmitters are off when it's in eclipse. But we can see it's getting towards that point where the battery life is definitely showing itself. UCube 1 from the UK Space Agency, prime contractor there was Clyde Space up in Glasgow. That reached the end of its mission after about 3.7 years in space. And we know that the probable cause of that was battery failure. It used lithium polymer batteries, which are these flat pack ones. And we have one single telemetry point. So this is not definitive, but we saw the battery temperature rapidly increasing just before the transmitters failed. So probable battery failure on that mission. The von Karman Institute's satellite, EO-79, had a linear transponder on board supplied by AMSAT-UK and AMSAT-NL. The mission from an amateur radio perspective went on for about 6 months. What we learned on that one is measure your power supply usage very, very carefully indeed. When the transponder was switched on at the end of the evaluation of all the test instruments on board, we found that the battery was draining even when the satellite was in the sun. So we had a negative power budget. Some clever people at ISIS Space in Delft wrote some software patches for the satellite, so we would switch the thing off in eclipse, wait for 10 minutes when it got into sunlight, and then switch the transponder on for about half an hour, and then turn it off so it had a bit more time to charge the batteries. That worked well, but as the seasons changed and the orbits precessed slightly, it became impossible to justify all the time given for free to write the patches to keep that satellite running. So an interesting experience, and 6 months, but a negative power budget, so if you like, another battery or EPS failure. The bottom ones there, EO-88, Naif 1 from the United Arab Emirates is still going strong. 5.6 years later, that's as good as the day it was launched. JO-97, a partnership with Jordan. That satellite appears to have had a microcontroller failure, which would normally spell the end of the mission. But in our case, we have an architecture where we don't rely totally on the microcontroller for all the functions. And above that, in a sort of hierarchy, we have a state machine, which is a Xilinx CPLD, which acts as a command decoder. So even if we have a microcontroller failure on board, we still have some very limited access to control the payloads. And that's been a lifesaver, frankly. It's the equivalent of pulling the plug out of the wall on your PC and then plugging it back in again. It solves a whole host of faults. So 3.8 years and counting from the launch of JY1sat on the Falcon 9 from Vandenberg. And on that same mission was ESEO, the 44 kilo satellite from the ESA Education Office. That is now at end of mission. I've put down 0.041 years. In fact, the amateur radio payload on that was active for, I think, 3.5 hours, which, if you calculate, comes out of that to keep the units the same. The reason for failure there appears to be multiple design issues on the platform. Everything from communication systems, computers, and even we noticed our mission when it was finally switched on started out at -16 degrees centigrade. So if that was typical of the temperatures on board, then possibly that wasn't doing the batteries on board ESEO very much good. So 6 data points. And if you know a little bit about reliability, there's something called a bathtub curve. You familiar with that? So it's time on this axis and failures from 0 going upwards. And in a typical lifespan of a system, you start off with a sample where you have a lot of failures due to perhaps manufacturing errors or design errors. You then enter into a period with very low failures. That's the normal lifespan of the system. And then as they reach end of life, the failure rate begins to go up again. And I only looked at this a few days ago, but actually we've got the beginning of a very nice bathtub curve there. So we've got SAO failing after a very short period of time. We've got EO-79 lasted a little longer before we discovered the negative power budget issues. But the other satellites are nicely coasting along that highly reliable zero fault area until they reach the end of their life. So I thought that was quite good. The important thing here is that over 10 years or so, we've accumulated 22 years of cumulative time with some very key systems of the things that we've built. 70 centimetre band receivers, the linear transponder, the 2 metre PA, and several other parts of the satellites have worked failure-free on all of the missions that we've put on. So we can take some comfort in that some things we've designed now have quite a lot of heritage. So let's have a look at Funcube Next. After 10 years or so, it's about time AMSAT got into designing and launching another satellite that it can design and manage for itself. It's at a very early stage in the project, so we're really at mission definition and initial design. And what we've come up with so far is that what we will try and create and launch is a 3U CubeSat. So it'll be something that we haven't done before. So 30 centimeters by 10 by 10. And there's a very good reason for doing that. Firstly, as you increase the mass of the payload, you get more thermal stability. AO-73, for example, suffers a 50-degree change in temperature between when it's in sunlight and at the last point of eclipse. And if you can imagine, it's done something like 45,000 orbits. And on every one of those orbits, things inside are expanding and contracting, expanding and contracting. And normally, that would be something that would lead to premature failure. But it seems to be working okay. With a 3U structure, the temperature changes because of the mass are rather smaller. So a 3U satellite will be more thermally stable. It's, of course, a greater volume, so we can pack more things in it. And interestingly, it might offer us a greater opportunity to find a launch. Most satellites these days that are launched in the CubeSat category tend to be 3U or 6U. Now, it doesn't happen very often, but sometimes people say they're going to deliver a satellite to a launch agency, and in fact, they can't meet the deadline. And so that launch opportunity becomes available. Never nice to see concrete blocks or bits of aluminium launched into space that don't do anything, just to have the mass right on the rocket. So occasionally, opportunities like that come up, and that's another reason for going for a 3U satellite. We've also decided that we can, at the moment, fit 3 amateur radio transponders on there very easily, based around things that we've already done and have quite a lot of flight heritage. We'll retain the 1200 bits per second educational outreach telemetry. I work at a school part-time, and every summer I do an after-school club with the sixth formers, and we're out making Yagis, pointing it at the satellite and picking up data as it flies overhead. And AO-73, with its forward error correction, is very, very easy to receive on the ground by people who, are waving aerials in all sorts of directions. It's a very reliable educational outreach tool. So we'll retain that basic format. We will probably update the error correcting code, though. We use something that was adapted from Phil Kahn's AO40, forward error correcting techniques and telemetry format. We sped that up from 400 bits per second to 1200 bits per second, but made 0 other changes. And perhaps after 10 years, we have to stop apologizing to Phil and come up with something that's a bit more up to date. What else is going on Funcube Next as a project? Well, we thought a wide-angle camera would be very nice. I've said high definition, but in fact, somewhere between 6 and 10 megabyte images. That will give a fair degree of definition. They should be very nice to download from space. as those images are quite large, we need to do something other than have a telemetry system that just works on the 2 meter band. So we are going to put an X-band downlink on this satellite. It'll be a data downlink only. We don't anticipate having a transponder for amateur use, but it will be a method of getting these signals down. And the nice thing is, with QO100 in operation now, there are a lot of stations around the world with 10 gigahertz receive capability. You might have to take the LNB off the fixed dish, prise it off there and point it at the sky. But with any luck, when the satellite goes overhead, an LNB, perhaps a small horn antenna, should get you some data from this satellite. And we're hoping to encourage people to have a go at that. Because we're using 10 gigahertz, we now have to have some form of attitude determination and control system. Previously, on the other missions, we quite often just had a magnet in the middle of the cube. And if you can imagine, if I've got a magnet going north-south here, it will follow the Earth's magnetic field. So we have 1 degree of attitude control, but unfortunately no control at all around it spinning on its own axis. And at the moment, AO73 is doing 1 revolution every 3 seconds, which makes it a bit challenging on occasions to get a QSO through it. So attitude determination control system, we don't need something that points within a couple of degrees at the ground station. So we don't want to use up lots of power or use lots of difficult techniques to do this. We only need to keep the, if you like, the X-band antennas pointing roughly in the right direction. So perhaps nadir pointing straight down towards the center of the Earth, or perhaps towards the ground station. 35 degrees is all we need, because that's half the beam width of the antennas. So it's important not to over-specify systems like that, because you end up spending an awful lot of money and doing an awful lot of work when you don't actually need to get it targeted to within a few degrees. We've also taken the decision to separate the flight computer and the payload or experiment computer. And the reason to do that is just to separate the tasks out. And if you look at the line underneath there, we want to give the opportunity to fly your own code. We're aware that on our missions we've gathered a large amount of data, but we very rarely process it to see what's contained in there. If we offer the facility to students, or I think what's the modern term, citizen scientists, to write code for the payload processors, first of all it means anything they write won't affect the flight control systems, but it will allow people to access all of the sensors on board the satellite, perhaps things like the camera, solar panels, sun pointing things. We've got RSSI, so you could perhaps model the usage of the various receive frequencies on the satellite, and you can begin to process data like that. The only time we really use that data is if something goes wrong and we say, oh, what's happened there? We download the data and then we examine it. It would be much better to have that data out in the world and allow people to do their own experiments on the satellite. Radiation. There have been a number of missions that have tried to measure total ionizing dose. That's quite a common payload to put on board. We thought something more akin to a Geiger counter, though, so a rate meter, where you get a particular count of radiation over a given period. And we thought about a minute. So what we're going to try and do is set up a radiation sensor, put the electronics on board, and download the amount of counts per minute we receive in orbit. And again, that's a great opportunity for somebody to do some research, work out where the satellite is, look at the data that's being collected by the radiation sensor. You might be able to pick out things like the South Atlantic anomaly, where radiation at the Earth's surface is much higher due to variations in the magnetic field. poles, things like that. So the ability to plot radiation around the planet as the satellite orbits. We've also got the opportunity with modern DSP techniques, which in 2013 consumed oodles of power. Now you can do those processes with much less power consumption. So it's possible to take one of the signals out of the receiver, digitally process that, and perhaps changing the format, and then retransmitting it back down to ground. So there's the possibility for digital communications which can be programmed on orbit. So that might be a very interesting way of updating the communication systems as the lifespan of the satellite goes on. We've got these large images from the camera, but we've never had an X-band system flying in space before. So we need a plan B. And plan B is to try and come up with something rather like the system used on QO100. There's now an experimental beacon that crams quite a lot of data into a relatively small bandwidth. What we're trying to do, purely as a backup, 2 meters is quite crowded, so a backup only, is we're trying to generate a system that can transmit 19K2 down to the ground in a relatively small bandwidth. And if we can do that on 2 meters, it means we've got some degree of reliability. If X-band fails, we can still get that data down. Incidentally, if you have a 10 megabyte image, to get one block, say you divide the image up to 256 blocks, at 19K2, it'll take 16 seconds to get one of those 256 blocks to make up a high definition image down to the ground. What do we do? Daniel was doing the talk just before us. I said, would 8 PSK possibly work in low Earth orbit? The answer is we don't know. QPSK might be the answer, but an evolution of telemetry. So we are all radio amateurs, and we like talking to each other via satellite transponders. The AO73 transponder, in simple terms, looks rather like that. 77's receiver, a linear transponder with all the filtering and AGC. I think it's about 45 dB of AGC in the Funcube transponders, a 2 meter up converter, and then a 2 meter PA, about half a watt output typically, something like that. If we reproduce that, which I think we should, we've got a nice linear UV transponder. But linear UV transponders are not the easiest thing to start out with in terms of amateur radio satellites. In the States, everybody likes FM. Couple of Bofang handhelds for £35 each, transmitting on one, receiving on the other. That's become quite popular as a low-cost entry point into the AMSAT world. So if we use some of the common points in our UV transponder, the linear one, we can actually take out an IF signal from the 77's receiver at 70 megahertz, put on an FM receiver at that point. We know the 77's receiver is extremely reliable. We can put on an FM receiver there. We need to take the output of that into something like a CTCSS, which is a low-frequency tone encoding system. We need some timers to make sure that doesn't drop out. And we also need some logic, so in case that system goes wrong, it can be bypassed by the onboard data handling computer. So we've got to develop that CTCSS block. 2 meter FM transmitter, well, we actually had one of those flying on ISAO. It never actually got switched on, but it's done lots of lab time, and it's done lots of time in the environmental testing, so it's been through vibration testing and thermal vacuum testing down to -20 and +60 degrees, and worked fine. And again, we can switch that into the same 145 megahertz PA, and we can have FM UV available without much extra effort. So you know how it is. You look at something like this with a bunch of friends and somebody says, but what if, and of course that can get out of control. But there was one good idea. And that is, let's add something on 24 SEMS. It's one of these bands where if we don't use it, we're going to lose it. We might lose it anyway, but let's use it and lose it if we have to. We have some issues with compatibility with the Galileo GPS system. But nevertheless, 24 SEMS from 1260 to 1270 megahertz is allocated to amateur radio. And we can generate something quite easily for that band. It needs a separate antenna, so if there's any mechanical engineers in the audience who fancy a go at an L-band receive antenna, that would be great. But in terms of integrating it with the previous two transponders, it's fairly easy. It's a duplicate of the CT-CSS added to the end of a 24 SEMS receiver, and then that can be just switched into the 2 meter FM transmitter that we've got in the transponder above. So that's where we are at the moment. It's an initial design, but most of that has been built and tested already on other missions. So we think it's a viable thing to do. That doesn't mean to say that will be the only transponders on board, but it's where we are at the moment. In fact, we're nowhere near filling up that 3U of space. So there is plenty of space available within that frame to get more experiments in. Of course, just to complete it, there are those other two things that need to go on this communications block diagram. We've got a 3 centimeter transmitter, which is essentially an IQ modulator, giving us the X-band data downlink. And up at the top right there, if we're going to try this new data system as a backup for high definition images, then we need to do something on the 2 meter band. And again, an IQ transmitter directly wired into the onboard data handling system will be able to generate signals that can go into the PA and come down on 2 meters. So that's where we are at the moment for transponders. So let's have a look at some of the hardware we've produced. Top left-hand side is the stack of 3 boards that have flown on several missions. Essentially a transponder board on top there with the receiver, the transponder core with all the AGC in, and the 2 meter band driver. Underneath that, there's a separate 2 meter power amplifier. All of these have got multiple telemetry points on there using I²C. And right at the bottom is our own, if you like, command and control system, which is on these boards an 8-bit processor and that Xilinx CPLD that's got us out of trouble on so many occasions. So that's flown on 1, 2, 3, 4 different missions, very successfully, 0 failures. On the right-hand side is 2 L-band receivers that flew on the SAO mission. So even although these things weren't used very much in orbit, we had the ability to spend some time developing them, get them fully tested. They went through ESA approval systems, which was a very interesting and quite demanding exercise, taught us a lot. So 2 L-band receivers on one board at the top right. That was going to be the L-band L-band to VHF FM transponder on SAO, and the other channel was command and control. At the bottom right-hand side, 2 meter BPSK transmitter on SAO, along with a 2 meter FM transmitter, again, went all the way through the testing process, and that board ran for about 3 hours, 30 minutes in orbit on that mission.
It didn't fail.
It didn't fail. It didn't last very long, yes. The computer switched it off when it decided it had enough. And lastly, and I think this was very good from an earlier presentation, it's important that we encourage the younger generation to realize the benefits of AMSAT. What we've started to do is to sponsor students at Surrey University with their degree level and MSc projects. So we've, for example, got a student, Patrick Hope, who incidentally is Mike 6 uniform Mike Papa. So amateur radio, alive and well at the University Space Engineering Department. Patrick's been developing an X-band system, has yet to be fully tested. He's done some initial tests on it. Being X-band, it's a fairly exotic dielectric. He got as far as this and some basic testing during last year. It's October now. There'll be a new group of students taking this project on, and hopefully in a couple of months' time, we'll talk to our friend and colleague, Chris Bridges from SSC, and we'll see how far the students have managed to progress with this. So getting support from academia is really important. It encourages students into the AMSAT world, it promotes communication, but it also helps with their degree level projects. And if we can finance something like that, it also benefits AMSAT. So it's something we want to continue with. Okay, we'll just have a quick look at this wide angle camera idea. Wide angle, about 150 or 160 degrees. The idea is to take a commercial camera, so nothing really exotic, but adapt it for space. And by adapting it for space, I mean things like removing plastic lenses, because the molecules tend to fly off them in a vacuum, and you end up with images that look like you're flying through a cloud after a fairly short period of time. So a few modifications required. Data available on X-band, looking at about 100 kilobits a second, which is not fast, but we wanted to make sure the ground stations weren't too over-specified. It's no good saying, oh, we've got this lovely data coming down from space at a really fast data rate, if you have to use a dish that's so narrow you can't possibly follow the spacecraft. So about 100 kilobits a second is a target for that system. Modified commercial camera. Data for images will need greater than one pass. So we don't anticipate you being able to download a single image in a pass, but we plan on breaking the image up into maybe a 16 by 16 array. And then, just like we do with our telemetry, people can get a block of that data. It will be perhaps sent to a data warehouse where it's stitched together with other people's data. It will also display on your local PC. And if you can imagine something like the telemetry counter on the left-hand side, where if you receive a block of telemetry from AO73, your name comes up. We could, perhaps do something like that. So a block of an image is credited to the first person who downloads it. So, it's a team effort to try and recover these things from space. Raspberry Pi, here's an example. First tested by SSTL in Guildford, and the camera payload developed by one of the students at Surrey Space Centre. Let's have a look at this. So if we have a look at that, it's not as high a definition as some of the modern cameras. It's one of the earlier Raspberry Pi cameras. But on here, sorry about the lights, we've got Corsica, Sardinia. On the far side, we've got Italy, quite clear there. We can see the whole of the Adriatic from Slovenia down through Croatia and beyond. And right at the bottom here, we've got, I think, Tunis and the North African coastline from Tunisia down to, is that Algeria, I think, at the top? Somewhere like that. So if we could get some images rather like that, not sure how many days we'd have to wait to get a clear day like that over the United Kingdom, but there could be some other places of interest around the world. I think we'd be very pleased to be able to download live images from space rather than what we've done in the past, and that's have stored images on board the spacecraft that are then sent down. So I thought that was a very good example. Finally, let's have a look at this radiation sensor. We wanted a radiation sensor that we could use as a rate meter, so it needs to have, a pulsed output that we can count. Traditionally, a Geiger counter would use a Geiger Muller tube. Can't really use those in space. They need very high voltages, They're quite fragile. They've got a little thin mica window at one end, which undoubtedly would stop working within the first few hundred feet of a rocket launch. So we had to come up with a solid state alternative, a silicon detector. This one, the BG51, is made by a company in Switzerland. It's based on an array of pin diodes. Pin diodes have a layer of P and a layer of N material separated by an intrinsic layer. And as radiation penetrates that intrinsic layer, it releases particles, holes and electrons, which allow current to pass from N to P layers. This device counts those, amplifies that signal. There's a comparator inside and the TTL output stage, and it simply gives you pulses every time it detects radiation entering that intrinsic layer. It's relatively small. It's about 34 millimeters, I think, by 22. Not the smallest device I've ever come across. And it's obviously encapsulated. If I was to cut one of these open, I'm sure I'd find some very familiar components. I did write to the company and say, please tell me there aren't any electrolytic capacitors inside this thing. And they said, yeah, we can confirm that there aren't. So that's a good start. This device is sensitive to beta, gamma, and X-ray. Beta gives me some hope because beta is in fact an electron. Most of the radiation in low Earth orbit are charged particles, and even although this device can't detect alpha, it's really because it has to be enclosed to protect it from electromagnetic fields from the other transmitters on board. EM radiation can give a false count. Equally, I suspect, if you allow too much light into those diodes, that will also saturate the thing. So it's got an enclosure around it, and that will keep out alpha particles. But I suspect if something arrives with a fair degree of energy, 50 keV or above, I think that will penetrate the material that's surrounding it, and we will be able to detect those particles in low Earth orbit. Disadvantages. The active area on this is quite small. So if you can imagine a Geiger-Müller tube with perhaps a 2 centimeter diameter active entrance at the beginning of it, this is something like a 20th of that size. So the background radiation count, the ability of it to detect particles is reduced. So we'll get fewer counts per minute, but it looks like it's going to be a really solid device and should survive the rigors of launch. Okay, Graham, I wonder if this will work. Let's give this a try.
So this is a test of the BG51 radiation sensor. The idea is it should be able to detect beta, gamma and X-ray. This is a little test board I've made up here. That's the
We've got
BG51
moving images
in
on
the
the
rectangular
monitor
box on
and
the
a fixed
left-hand
image
side.
on here.
And on the right-hand side is just a 5-volt regulator, 7/8L.
Okay, so I'm going to talk my way through this. I work at a school. We've got a physics lab. We've got limited access to some radioactive sources, which is quite good. I decided to give this a bit of a test. So went in one evening after school, set up an oscilloscope, power supply, and a beta emitter, which I think was strontium-90. Sat the detector, which just needs 5 volts at 25 microamps, so it's ideal for a CubeSat project. There's hardly any power consumption there at all. And went through the process of seeing what would happen. And sure enough, about 20 centimeters or so away from the detector, the oscilloscope showed some beautiful pulses from 0 going up to 5 volts, TTL levels, and the whole thing appears to work exactly as advertised. I'm not sure we can actually detect or determine rather what type of radiation is being sensed, because the only change is the pulse width. And that doesn't really tell you what type of energy, what type of radiation it is. It's more a measure of the amount of energy the photon or the particle has when it reaches the detector. So we'll have to do some more experiments with that, but so far that appears to be absolutely ideal. That detector's not rare. If you go to DigiKey, they actually sell a kit with that thing in it as a Geiger counter, but it does appear to be very reliable from the limited testing that we've done so far. And with that,
Low 5. Got a scope probe connected.
okay, with that, there's only one more slide, and it says, thank you very much. Are there any questions?
Thank you for that very informative talk as to where AMSAT's going with Funcube. Can I have any questions from the floor? Gosh, lots. First up.
Hello. In terms of the transponders, what sort of power budget in terms of supply are you looking at to do all this?
Well, remember we've got some very good figures from the existing 1U CubeSats that are operational, AO73, EO88, JO97. We know exactly how much power they use. I can't remember off the top of my head what it is, but if it works okay on a 1U satellite, then on a 3U, where we have all that extra space for solar panels down the outside, certainly that will work as well. We would be able to turn the power up a bit from where it is at the moment, and we would need to consider that because the lifespan of the satellite really depends on the depth of discharge of the batteries. We have to keep that really small if you want to get that multi-year lifespan. I think with AO73 it's still working almost 9 years on. The batteries are 6 to 7% depleted in eclipse, and that's a really low figure, and that's the secret to long life. So we won't push it, but we can nudge the power up a bit.
Okay, next person with a question, please.
Is there any chance to have a live image coming, maybe with a smaller resolution, just to simulate how meteor satellites work, or maybe build something fancy about it?
The difficulty with live images, as you say, is resolution. Depending what we can get down on the X-band downlink, that's certainly a possibility. Most of these cameras have still images as an option, but really they're intended for video downlink. SSTL have a lovely little video, I'm so glad I didn't use it, showing a moving image of that exact same camera over Denmark and the Baltic. So yes, it may be possible. It's one of those things we have to experiment with and see what the data rate has to be to successfully achieve that. We could pre-record things. We could perhaps time the camera to come on. It could record a few seconds of video, and we could download that at our leisure. Just think separation videos. That might be quite nice.
Okay, thank you. Jules.
On the power budget again, what battery technology are you thinking of, and is there any thoughts about using, say, folding solar panels to increase the power budget?
I'm not sure about the solar cell technology. I think we're still on triple layer cells at the moment. Okay, battery technology, at the moment I think we would certainly go with lithium ion, but we would not go for the flat battery packs that can expand. I've certainly had a phone that's popped open when the battery has decided to give up the ghost. I think lithium ion actually inside a sealed container is a much safer way to go. We haven't seen any failures of that type of battery technology. The lithium polymer packs, we have seen several failures for no apparent reason.
Folding solar panels?
Sorry?
Folding solar panels?
Oh, deployables.
Okay.
Might be a
Someone
step
else?
too far.
Just a question about around the microcontrollers. Had you thought about using a field programmable gate arrays instead of a microcontroller?
Yes, it depends on the degree, and I'm speaking here as an RF engineer rather than somebody who knows anything about computing, but certainly FPGAs, if we can get the right low power budget, would be a very good way of doing that signal processing, especially if we can upgrade the programs in orbit. That would be an excellent choice.
Okay.
Okay. You've heard this before, David, but some of the others might not have done. I think the fitter message idea on Funcube 1 was a pretty good success. We're still uploading messages, although not that many. It's tailed off in recent years, probably because the novelty's worn off. But I would put it to you. Would you? Two questions really. Would you do that again? Would you consider the ability to upload pictures so kids could see a picture of themselves or their school or their favourite teacher or something like that?
As an RF engineer, Jim, it's only software. So yes, it's one of those things that we need somebody to develop, but certainly ideas like that are what we really need to take this project forward and come up with some definitions for good educational outreach or just general interest, frankly.
Okay, one more question up here.
Okay, two thoughts. First of all, I understand the FCC are getting quite interested in end-of-life deorbiting.
Thank you.
Which might be a bit of an issue. Mm-hmm. Second question, and this is just a thought from the hip, is there any possibility or any benefit from having a shortwave or medium wave type of detector in order to work out what the absorption is for propagation prediction works, actually doing from ground to the satellite, and just try and, is there something there that might be of interest?
Second point first, that's a very good idea. I think AMSAT North America ran a programmable, it may have been some form of ICOM radio on one of their satellites, and indeed you could program the frequency from the ground, and I'm not sure you could get the modulation that was coming out of it, but you could certainly look at signal levels, and of course you can calibrate that so you can get the real signal level at the satellite if you do the pre-calibration before launch, and then you can compare the expected field strength over a distance. So that is a practical thing to do. I'm struggling to understand why I would do that. Certainly ionospheric absorption, as you say, would be a good reason. We'd need to look at that, but yes, a good idea. First point, very important. The legislation surrounding small satellite launches, as you say, is tightening considerably. The FCC have come up with a proposal, I think it's only a proposal of rulemaking at the moment, that anything should deorbit within 5 years of end of mission. For us, I think we could safely claim, okay, 10 years plus 5 is 15 years, so let's look at orbits that have a natural decay rate of 15 years. But that is the FCC. They tend to make up different policies fairly randomly. I understand they also won't license anything now that's smaller than 10 by 10 by 10. But we've heard from several presenters earlier today that pocket cubes, pico cubes are becoming more popular. So it seems to be excluding a whole raft of technology for no real reason, because I believe as we are upgrading technology, they are also upgrading the ability to trace or track smaller and smaller objects in orbit. Incidentally, AO-73 isn't licensed in this country. It might have been a project managed and designed within the UK, but AO-73 in 2012 was pretty much impossible to license under UK regulations at that time. The cost of insurance and the admin from the regulators greatly exceeded the entire cost of making the satellite. That's changed, to be fair. UK Space Agency and the CAA now have a traffic light system. I think if you were to deploy from the International Space Station, it would probably be very reasonable indeed. We would love this next satellite to be licensed as a UK space object, and we'll certainly pursue it. but I'm not terribly hopeful. I had a look through the list of UK space objects in the registry that was updated, I think, in February this year. I can't find a single university satellite anywhere in the UK between now and going back to 1990. So I think that says how difficult it is to license things here in the UK. In contrast, the USA, they're launching things from university about once every 6 months on the Alana program. Hundreds of universities have had things launched by NASA and the Alana program from NASA. Yeah.
Okay, we have a question over here.
On the Funcube, you have heat radiation experiments to replace Leslie's cube.
Yes.
Are you planning to repeat that?
If we did, we would certainly improve it. You can just about see, Leslie's cube is an experiment to show heat radiation from different coloured materials. So we have an anodized black piece of material on one of the solar panels and something that's bright silver, and you're supposed to be able to see the difference in temperature as heat radiates away from them in eclipse. You can, I'm not sure it tells us much, and I think that's basically down to we weren't able to isolate those metal panels as much as we would like from the rest of the satellite, but it's a nice idea.
I think there's one other question.
Quite a few online. We'll come back, okay, after this.
Thank you.
It's Martin Satch, IARU EMC. I hear noises about satellites being put into orbit, picking up large amounts of solar power and beaming it down to the ground. Have you thought about the immunity of your satellites as they pass through the beam?
Our satellites, remember, have quite an EMC problem of their own. On a satellite that's only that big, that contains a transmitting antenna separated by 10 centimeters from a receiving antenna, you have to be really good with the ability to handle high-level signals. And of course, the filtering on board is much more extensive than you would think. So I'm fairly confident that providing there's a reasonable distance between any such source, I don't think it will damage the satellite. Remember, you can do things like you can put pin diodes across the input, so even if you transmit a watt into it, it can still safely survive that. It's all in design. Design for failure. Work out the worst situation and mitigate it.
Okay. Thank you. We've got some online at the moment. I'll hand it to Graham.
Yeah, thank you. Akim says, greetings to all. DH2VA. Do you need to acquire a license, brackets from whom, to take images from space?
We're not in the USA, so I don't need to go to, I think it's NOAA in the US who have to issue licenses. I believe we can fly a camera without any particular issue. Of course, the circumstances will change depending on the country of license.
Okay, one from Gerard. I'm not sure who Gerard is, but greetings to Gerard. Great presentation. Thanks, David. 2 questions. 1, any ideas to augment the radiation detector experiment to detect different kinds of radiation like TID, for example, using RadFETs? Question mark.
Haven't thought about that. Just gone for this one so far, but it would be really nice to be able to determine what it's detected rather than just the energy of the incoming radiation.
And second question, how would one go about joining the team? What kind of disciplines are missing?
Our team is quite limited. We tend not to design stuff that we are not very familiar with or we don't have experts in. We tend to buy it instead. So if you want to reduce our bill to other companies, just let us know what your skill sets are.
Okay, thank you. One from Max M0VNG. Thanks for a great presentation. Glad to see we're looking at VU FM alongside AMSAT-NA to encourage new operators onto the birds. How much are we looking at cost-wise? Could we do a build one, get one freestyle approach rather than a one-off payload?
Yeah, I haven't found a buy one get one free available from any agency that I know. On the other hand, if you can get an Alana launch, we'll happily stick a this belongs to you DIMO label on it, and you can fly it as a US satellite.
Okay, well, I better wrap it up. Thank you very much, David, for showing
Thank you.
appreciation. Yeah.